All right, so I realize actually that a better title, given the context of the conference, is probably compiling fault-tolerant algorithms and material simulation. And so a couple of times people have mentioned things like block encoding costs, where they're talking about asymptotic complexities of algorithms. And so I'm going to talk a little bit about actually what those costs are and actually compiling for fault-tolerant quantum computers. So this work is motivated by this question that kind of Garnet alluded to this morning, looking for a quantum simulation advantage in physical simulation, so for chemistry and materials. So there's been a couple of examples where we have cost out the fault-tolerant algorithms, at least for the problem of sampling from the eigenbasis of a particular Hamiltonian, for some challenging chemistry problems. The kind of canonical example of the field is this nitrogen fixation enzyme. And so this is the FOMOCO problem. And in this paper, my colleagues have worked out that it costs about 4 million physical qubits and 4 days of runtime. This is assuming a surface code architecture. And so that's pretty good. It's below a gold standard 100-hour calculation. We continued this kind of work addressing whether this kind of hype question about quantum computers and drug discovery, this P450 enzyme is responsible for actually digesting about 50% of the drugs that you take that are on the market. And similarly for this problem, we looked at the fault-tolerant resource estimates and got around 4.6 million physical qubits in 3 days of runtime. We also performed pretty extensive classical calculations to try to ascertain if there was a simulation advantage in the large kind of active space version of this problem. And so you can ask a similar question for an interesting materials problem. That's another area where quantum computers are expected, or at least cited, to be killer apps. And this is this lithium nickel oxide battery cathode. The characterization of the ground state is a little bit unclear. There's kind of a simple chemical question that you can ask. Does the ground state geometry of this have a Jahn-Teller distortion in it? And so we ultimately want to get to the fault-tolerant costs for this and whether there's a potential simulation advantage question here. Okay, so this work that I'm presenting also presents some algorithmic speedups. So if there's one thing that you take away from this talk for fault-tolerant algorithms for materials, it's that we get a group order quadratic speedup in simulating chemistry and materials Hamiltonians by exploiting spatial point group symmetries. A little bit more precisely, we get a group order square root speedup improvement in the block encoding of chemistry and materials Hamiltonians that are represented in second quantization. Okay, so the rest of the talk will pretty much be geared towards giving color to this and sort of describing where this comes from and how we do these fault-tolerant resource estimates. So the context is phase estimation. And so for that, it's been discussed previously in the conference. Our approach is going to be assume a good initial state. And we saw earlier that maybe this is not a good assumption, but we're going to start with it. And then we want to perform phase estimation, which would allow us to sample from the eigenbasis of a particular Hamiltonian. Of course, you can use the propagator for the system to do phase estimation, or there's some more recent methods where you phase estimate a different unitary, this quantum walk operator, which is generated by the arc cosine of this Hamiltonian divided by some parameter lambda that I'll introduce. And so this Hamiltonian simulation model uses a linear combination of unitary approach, which effectively means that you can represent your Hamiltonian as a sum of unitaries multiplied by a positive constant W. To do this, we use the qubitization framework, and really within this framework, there's two oracles that are quite important. First one is select, and select acts on a state that is composed of two registers. One is your state psi, the thing that you're going to phase estimate, and the other is an ancilla register L. Effectively, what select is doing is it's a for loop. So it says for any basis state L in your ancilla state, apply the ULth unitary of the LCU. The other oracle that we need to define to get constant factor resource estimates is this prepare. Prepare, apropos to its name, generates a state where the coefficients are the probability amplitudes proportional to the weights in the LCU. And this is where this lambda parameter comes in. It's this normalization that's required to do these block encodings. Of course, if you have a unitary and you do a block encoding of a Hamiltonian, the Hamiltonian that's sitting in this unitary needs to be a norm less than 1. Okay, and so the circuit that actually generates this walk operator W looks something like this. It requires 1 call to the select oracle, 2 calls to the prepare, or the prepare and inverse prepare, and a reflection. And so just from phase estimation, we know that the number of queries to this W circuit will need to scale as lambda over epsilon. The lambda is in the numerator because every time you're dividing the Hamiltonian, that's just scaling linearly the cost, right? And so we know that we need to make this many calls. That's nice, that's an asymptotic complexity, but we're really interested in costing out how difficult is it to make select and prepare, namely making these white box implementations. Okay, so in quantum chemistry simulations, we actually have a lot of structure that we exploit when building these, and there's a couple of quantum primitives that are very important. And the next kind of part of the talk, I just hope to show that compiling these algorithms is really like normal programming. You kind of have to change a couple of things in your mind. Everything is vectorized in some sense. So it's sort of like GPU programming. But you combine primitives to build up these kind of complicated looking circuits. And then you write these like 100-page papers, which is effectively writing the algorithm in English. Yeah, there's probably a better medium to do that. And we're certainly working on that. So the structure that we take advantage of in the chemistry Hamiltonian are these tensor factorizations of the Coulomb operator. Generically, you have your Hamiltonian. That's this. The coefficients are described in this 4 tensor, and they multiply the operator, this 4-mode ladder operator here. And that corresponds to some LCU. And you can kind of compress the information by various forms of tensor factorizations on the Coulomb operator. Right here, I've kind of written out 4 versions of this. This is in tensor network representation. Here, there's no factorization. This is a SVD on the matrixized version of this tensor. And here are 2 sort of hyper-contracted tensor network forms for the Coulomb tensor. So there's various factorizations, and we want to cost out exactly how we do the LCUs in each of those settings. And then there's some primitives that we actually need to define. So I said earlier that there's this select operator. That select is sort of like a for loop. And it turns out you can actually write this for loop as reversible logic in order L Toffoli complexity. Effectively, what this is taking a for loop and putting it on a segmented tree. And you can start just gluing these trees together. And so that's a type of a quantum data structure. And this has linear Toffoli complexity to do that select. And so that's an example of a primitive that we're going to use over and over and over again. The other sort of primitives that we need are getting data into our calculation. And so for this, we're going to use a ROM model. And effectively, we can use that for loop again. So here's that for loop bit up here, where at the bottom of the for loop, namely, we're just doing depth first iteration over this tree, we are actually just outputting all of the data that we need. And these are all just Clifford operations. And so again, this is either costing linear in Toffoli complexity, where the linearity is in the number of terms in the LCU. For this one, there's other variations of it where you can actually trade space for Toffoli complexity and time. And so we're going to kind of move between those two depending on which one is going to be optimal for our particular LCU. And the last I won't explicitly talk about is prepare. This uses QROM, and it effectively is this preparing amplitude state that we'll use in other pieces of the algorithm. Okay, so those are some primitives for block encodings. The other kind of things that are nice in terms of a programming perspective are looking at how you might add and multiply things. So once you can add and multiply, you can effectively perform anything in the algebra of maybe a series of block encodings that you have. So there's, of course, a way to add block encodings. This just looks like a recursive block encoding. That's here on the left. And there's, of course, a way to multiply block encodings. And so with these tools, we just kind of combine these primitives together and just build up these more complicated looking algorithms. Okay, so I'm going to actually give an example of this now. So let's take this example where we don't do any Hamiltonian factorization or any factorization of the coefficients of our Hamiltonian. So one way to get an LCU out of this is just perform Jordan-Wigner transformation. And so for there, we get a linear combination of unitaries, where unitaries are tensor products of Pauli operators. And so in this example, I'm going to show you just how to write down select. So here we might have this two-body term. Each of these Q's are Pauli operators. This is some real-valued coefficient. It looks sort of like this because of the symmetry structure of the Coulomb kernel. But what do we have is that we have just a bunch of summations and some Pauli operators. And so this just, again, is like a more complicated for loop, right? So in kind of abstract notation, this index is exactly how you would write a bunch of nested for loops. So here, this is a for loop over the spin variable. This is a for loop over the basis variable, another basis variable, another spin variable, and then we apply select. And so it turns out you can actually just write this. You can actually write out those for loops and then translate that to a quantum circuit, or you can kind of play a couple of tricks and try to optimize this further, and that's what we do here. We get these other kind of more complicated things once you start to look at different tensor factorizations of your Hamiltonian. So this is a kind of fairly complicated diagram. It's really a cartoon of what's going on in the circuit, but once you sort of get used to using the primitives, it's actually a lot easier to parse. And so in this example, this is one of those instances where we're adding together a bunch of Bloch encodings and then doing multiplication. And so let's take this factorization where we first matricize our 4 tensor and then do an SVD. Here we get some operator that looks sort of like this, and this is a summation over a bunch of other linear combinations of unitaries that is squared. And so that just uses the primitives that I introduced on the first couple of slides. And so there we have a prepare step that has a superposition over each of the sub-Bloch encodings, and then for that, this is a for loop again, indexing on each of those sub-Bloch encodings and doing the prepare over those basis states. And then this is exactly a cartoon for doing that circuit that I showed on the previous slide. And so these start to get quite complicated, but really kind of in words, they're summarized pretty succinctly as just a series of for loops and multiplications. And so we can just cost out the most expensive things, and that actually corresponds in this case to these 2 prepare steps. Okay, and so you can kind of like get more and more complicated, and the circuits sort of look more and more complicated, and they become more and more cartoon-like, but effectively they're kind of encoding the same set of algorithms. And so for this one, this is one particular version of the decomposition, and this is another one which takes it to a different logical limit. Okay, so going back to the original question of where we get this square root speed up in the group order, first I have to actually describe what group I'm talking about. And in classic electronic structure, we use group theory to reduce the calculation costs, either in representing the Hamiltonian or reducing the contraction cost for a lot of these classical heuristics. And so I'm not going to go into details of specifically how we do this. I'm just going to paint a pretty high-level picture of how this works. Let's say we're given some molecule here on the left. This is ethene, and we can look at the symmetry of this particular molecule. It has 3 rotation symmetries, 380-degree rotations. It has 3 reflection symmetries, all of which are orthogonal. And if we look up in our handy group theory book which point group this corresponds to, we can see that this is D2H, and indeed this is a very nice abelian point group. And from there, we know that we can actually express the one-particle basis of our system such that it transforms as the irreducible representations of this group. Okay, so that's kind of a complicated thing to say, but what's the consequence? The consequence is actually that you get a selection rule for the coefficients of the Hamiltonian, namely when are these non-zero. To give you an example, that 4 tensor, here's that 4 tensor that I was talking about previously on 3 orbitals, and it gets this Bloch diagonal structure here. And the selection rule is effectively whenever the tensor product of the irreducible representation labels for the orbitals contains the symmetric, completely symmetric representation. And so, yeah, if that doesn't mean anything, you can just summarize that as there's a selection rule and it tells you which coefficients are 0. Okay, so our goal is to extend a lot of the machinery in the chemistry case to the material setting. And we can generalize this idea of using a selection rule and group theory for the molecule to the material setting. And so in the material setting, we might imagine a primitive cell that describes our material, and we can imagine a supercell, which is composed of a lot of these primitive cells. And the symmetry operation is the translation between each of those cells. And so the selection rule there is actually very familiar in physics. It's a momentum conservation. And what happens in second quantization is that this corresponds to a reduction in the number of non-zero coefficients associated with the Coulomb kernel. And so we go from something that goes as nk, where nk is the number of images that we have in the supercell calculation, nk to the fourth, n to the fourth, where n is the number of orbitals in my primitive cell, to something that's scaled as nk to the 3, n to the 4. And so that's automatically an nk savings. It might not seem like much, but this can get pretty large as we try to converge simulations to the thermodynamic limit. Of course, this is used a lot in electronic structure. Actually, this is one of Garnett's papers. This is looking at couple cluster for a carbon material and showing that you can do a fairly sophisticated classical heuristic, EOM CCSD, and get pretty accurate band structures. And so the upshot of this is that we're going to use this selection rule to minimize the amount of information that we need to output for our quantum algorithm, for our block encoding. Okay, so I'm just going to give an example of this because, again, these diagrams get even more complicated, but the story is actually quite similar. So we can do a similar tensor factorization on this fairly complicated, now 7-index item. Rewrite our Hamiltonian as a sum of squares, right? This is this SVD thing, again, that I was talking about. And building up the algorithm is almost identical to that it was before, except we can use some of the symmetry information to only output the minimal number of coefficients that describe my Hamiltonian. And so again, we have this prepare step, and then we have a sub-prepare step, and this is again the most expensive bit. There's now some extra modular addition that we need to do to account for this selection rule, but then pretty much everything else is sort of the same as in the molecular case. It's just kind of a detailed construction of all of these algorithms. So hopefully that's sort of paints the picture that, yeah, these circuits are kind of cartoon-like. They don't have all of the detail, but they're just kind of describing the algorithm at a fairly high level. And once you sort of get comfortable with these primitives, you can cost out all of these block encodings pretty easily. Okay, so what is the kind of conclusion of doing this? Well, we took the last 4 years of algorithms development in chemistry simulations, and we pretty much applied symmetry adapting to all of those algorithms. And in each of those cases, you get a scaling that's about the square root of the amount of information needed to specify this particular tensor factorization of the Coulomb kernel. And we get a square root speed up by using this selection rule from the group theory of the point group of our molecule. For materials, this is just the translation operator. So for these two methods, the sparse and single factorization prepares the dominant step, and we get a square root speed up there. For these two hypercontracted forms, we actually, for this one, we get a square root speed up, and for this one, we actually don't. This one is actually already optimal. You cannot improve unary iteration beyond linear cost in the basis, but we do get other savings, like reducing the number of controlled rotations overall. And so asymptotically, this doesn't have a speed up, but we'll see there's a pretty big speed up in the kind of small group order size. Okay, so that's kind of talking about how we'd actually program the device. Now we want to see what would this look like for realistic simulations. So let's just take a sample of some pretty simple materials. These are all kind of small unit cells. And we can generate their Hamiltonians in some reasonable size basis sets. When I say reasonable size, these generally have 30 to 50 spin orbitals, or 50 to 100 spin orbitals. Some even larger than that, but that's pretty much what is needed to get very good accuracies in a property like the bulk modulus of a material. And so we can then look at the scaling of each of our algorithms once we've compiled them all out. So effectively taking those cartoon circuits and then writing explicitly the circuits for all of them. Of course, we don't generate the circuits for all of these. We kind of have here some just general costs for combining them, but it is just effectively compiling the thing all the way down to gates. we see actually that there's this square root nk speedup isn't always exactly apparent. And this is because the total cost really comes up, for the algorithm, shows up in terms of the block encoding cost times this lambda parameter. Remember, we were rescaling our Hamiltonian by that lambda at the beginning. Okay, so this one is the sparse term, and here we would expect a square root speedup, and it's a little bit difficult to see. The x-axis here is the number of primitives in my supercell calculation. For this single factorization form, it's quite clear that there's this gap. For these two, for these two, the gap is also there, but it's numerically difficult to see, or it doesn't show up until a larger number of k points are used. Again, remember I was saying that for the tensor hypercontraction form of the Coulomb kernel factorization, we didn't asymptotically expect to get a speedup, but actually in the small supercell size, we actually do see a speedup because we are reducing the total number of rotations. And so that's kind of something that shows the difference between just doing asymptotic algorithm development and actually compiling these things down to gates. Okay, and so on the right here, this was actually the diagram that I wanted to make for this paper, kind of at the beginning of the project. Effectively, it shows you the gap for an interesting problem when you use symmetry in your quantum algorithm and when you don't. And so generally, we have this square root speedup in the point group, and for materials, the point group is just the translation operator. And so with a 2-2-2 sampling of the Brouillon zone, you might get something like a factor of 3, but at 4-4-4, you might get something that's closer to an order of magnitude, which is starting to look quite interesting. But even with this speedup, for realistic basis set sizes, and these systems are not converged to the thermodynamic limit in any sense, it looks pretty challenging in terms of the quantum resource estimates. And so this is just kind of a summary table. What's really important here is the right diagram, where these are the number of Toffleys that are required to perform phase estimation, so not just the block encoding, but the total phase estimation. And each line, the red is the single factorization, this yellow is this sparse, and these two down here are the hypercontracted forms. What's interesting is that this double factorization, you see that the dashed line, which is the unsymmetry adapted case, is actually below the symmetry adapted case. And so I was just arguing to you that I was getting the square root speed up, so you might say, well, what gives? That doesn't show up. And the case here, again, is where lambda actually increases for this particular problem. And so there's definitely a subtlety when you cost out all of these algorithms. You have to be kind of careful. Okay, I'm just going to conclude. So even with symmetry adapting, the square root speed up in the group order for material simulation is really nice. It's not enough, though, but this is just the first step. So there was some great work from Riverlane that kind of spurred this work, and we kind of followed up on a couple of different versions, and that's all of those different tensor factorizations. But then we can now look at other forms of the representation of the Hamiltonian. For example, in first quantization, you have a constant amount of information that you need to output to represent your system. Of course, there are other trade-offs. Your basis is much slower to converge there. So yeah, we symmetry adapted the last 4 years of algorithms for simulating chemistry in second quantization. This paper also is sort of long just because we developed some new classical simulation techniques. Namely, we symmetry adapted this tensor hypercontraction, and we did a large number of classical calculations, again, to try to ascertain, is there a simulation kind of advantage given what we know today and given the best classical algorithms. And so I'll just finish up by thanking my collaborators. These algorithm resource estimations are always kind of a huge group effort. And this work is between a number of Googlers, Dominic, and some external collaborators. That's it. Thanks.
Questions? Up there.
Thank you for the lovely talk. So as you alluded to with Garnett's results, the systems where you might actually expect to have a speed up, you may also expect the classical methods to have an equivalently good speed up. Can you talk a little bit about systems where you would expect a uniquely quantum speed up, where the classical methods don't also get better at the same rate?
Yeah, that's a good question. So everything in this talk actually assumes the best case scenario from Garnett's talk. That's like sort of the context. If you just, maybe I should have said this on the first slide or in the intro. Like, let's just take as like a given for this talk that you're in the regime where you can achieve the EQA hypothesis. And you have this constant overlap, but all of the energies are bad, right? And then we just assume that and just cost out all of the phase estimation part that goes after that. When you're not in that, I think it's much more difficult. We do a fair number of classical calculations also to like try to assess this question specifically, but it is pretty challenging for these super large systems. There just aren't so many methods that you can use classically at this scale. For the molecular systems, you definitely can make a much clearer assessment about the quality of the overlap, for example. In the first example, that P450, the overlap is actually quite good. And classical methods do improve quite rapidly. So there I wouldn't exactly expect a quantum advantage.
Thank you.
For the LCU decomposition, does it matter a lot how you split the unitars? Because you could, in principle, choose to implement not just Pauli words, but something different.
Oh, yeah. So all of the methods, I guess I'll do this one. All of these tensor factorizations admit different unitaries. So all of these are different. So for example, these two actually are sort of similar, but these two, they actually use the fact that the fermionic basis, you can represent vectors of ladder operators by a similarity transform of a single mode. And so that outer product effectively forms our unitary. And something similar happens in this particular tensor hypercontraction. And so you're exactly right that this LCU formalism gives you a ton of freedom specifically about how to actually construct the unitaries. And that's like part of the art of actually writing down these algorithms such they have low scaling.
So if you, let's say, make L capital small, would it help because you don't have ancillas and then you can reduce the depths?
You can make L capital small, but sometimes that comes at the cost of increasing the complexity of each of the U's to implement them. And so there's generally a trade-off.
Okay. Thank you.
Hi, I have a question about the circuit primitives that you showed at the beginning, where you called select a for loop on a seg tree, I think, and I wanted to ask what the seg tree is and
It is it's a classical data structure. I guess another way to say this is you can put a for loop on a binary tree and then do depth first iteration over that binary tree. But a seg tree at least maps over a little bit differently, but it's effectively a binary tree that allows like logarithmic cost updates and queries and sums.
Okay, I think I have to think about it.
Yeah, we can talk about it after.
At the very end, you walked through the specific costs that you might expect under a surface code implementation. Could you just briefly speak to what error rates and gate times you were assuming there?
Yeah, so for this, probably Craig is the better person to talk to, but we followed a kind of a similar model to the chemistry scenario where we're assuming a 1 microsecond cycle time, a 10 microsecond reaction time, and 1 × 10⁻⁴ physical error rate. Then there's some parameters that you get to play with in terms of like how many factories do you have, like what number of, how many times you're willing to distill something and the overall success probability.
There's enough information.
Yeah,